60 million pounds of dynamite. That is not a typo. 60 million pounds of dynamite detonated inside a 9-mile gash hacked through the spine of the American continent in a jungle so hostile it had already swallowed 20,000 men before the Americans arrived. 6,000 workers on a good day crammed into a canyon that reached temperatures of 120 degrees on the floor. With landslides that moved without warning, trains threading through every 60 seconds, and steam shovels swinging iron buckets the size of a small room through blasted rock, while the mountain above them trembled and watched and waited. This is the story of the Culebra Cut, and at the center of it, the answer to a question that had stumped the greatest engineers in the world for decades was a trick so elegant, it seems, almost obvious in hindsight. Put a giant steam shovel on rails, use the railroad to carry the dirt away, run the whole system like a military campaign, move a mountain faster than men ever had before. It worked. For 9 brutal years it worked. The question is what it cost them. Before the Americans, there were the French. Ferdinand de Lesseps was the most celebrated engineer alive in 1880, fresh off the triumph of the Suez Canal. He looked at the Isthmus of Panama, a narrow strip of jungle 48 miles wide, and decided he would cut straight through it at sea level. He turned the first spade of earth at Culebra in January 1881. He had estimates, projections, confidence. What he did not have was the right machine. His workers used handcarts and primitive excavators that could move barely 1,000 cubic yards a day. The mountain gave nothing easily. The rains came and saturated the clay walls until they moved like slow-motion rivers, swallowing everything the men had dug the week before. Yellow fever and malaria killed workers by the hundreds. Funding dried up in 1888. The French company collapsed in bankruptcy. By the time de Lesseps walked away, an estimated 20,000 men were dead, and the mountain had barely been touched. The summit of the Culebra Ridge had been lowered by less than 20 feet. Less than 20 feet of a 200-foot problem paid for with 20,000 lives. That was the inheritance the United States purchased in 1904. When the Americans took possession of the project, the partially abandoned French equipment was rusting in the jungle. The canals they had dug were silting over. A generation of investment and blood had produced a scar in the earth that was not deep enough to plant crops in, let alone float a ship. Here is what makes the American approach different. Not just the engineering, though the engineering matters enormously, but the thinking behind it. Chief Engineer John Stevens looked at what the French had failed to do and understood the central problem immediately. You could not move a mountain with men. You needed a machine, and not just any machine. You needed a machine that could bite through 8 tons of solid rock in a single motion, load it directly onto a train, and send that train away while the next one was already backing into position. You needed something that operated not like a tool, but like a weapon of industrial war. They ordered 102 of them. 77 from Bucyrus of South Milwaukee, Wisconsin. 25 from Marion Steam Shovel of Marion, Ohio. The first shipments arrived in 1904. Crews assembled the machines piece by piece in the Panamanian heat, bolting together boilers and boom arms and dipper mechanisms that had been built in Ohio and shipped to a jungle on the edge of the Pacific. When the first Bucyrus fired up in the cut and its boiler pressure reached operating range and the engineer pulled the crowd lever, and the iron teeth bit into the rock of the Continental Divide. For the first time, it was not a small moment. It was the moment the old problem met the new answer, and they sent them all into the gorge at once. The cut they worked in was quickly given a name by the men who bled inside it. They called it Hell's Gorge. We're going to find out why and how many men the gorge claimed before those shovels broke through. 95 tons of Ohio steel. Before you can understand what happened in that canyon, you need to understand what these machines actually were. Because calling a Bucyrus 95-ton steam shovel a shovel is like calling a locomotive a wheelbarrow. The word fails the object. It weighed 95 tons. That is heavier than the largest modern battle tank. It rolled on railroad tracks, its own tracks, laid fresh ahead of it by a 6-man ground crew every time it needed to advance. From the outside, it looked like a railroad locomotive mated with an industrial crane, all riveted steel plate and boiler housings and hissing pipe joints. The boom arm reached out over the work face like a scorpion's tail. At the end of it hung the dipper stick, a thick iron arm that drove forward under engine power into the blasted rock, and at the tip of the dipper stick sat the bucket, 5 cubic yards, 8 tons of material per bite. When it swung full into a waiting flat car and dropped its load, the car shuddered on the rails. Understanding how it worked means following the chain from fire to rock. The fireman fed the boiler. Coal went in continuously to keep the pressure needle holding steady. Not approximately steady, precisely steady. Because the steam demand was not constant. It spiked hard every 45 seconds, every time the crowd engine drove the dipper into the bank, and the hoist cable pulled 8 tons of rock up from the face. That spike hit the boiler like a hammer. Pressure would drop 3, 4, 5 pounds per square inch in a fraction of a second. The fireman had to anticipate it, had to be shoveling before the drop registered on the gauge, had to keep the needle from falling below working pressure, or the whole machine slowed, and the engineer behind him knew it immediately. You could hear the difference in the sound of the steam. A fireman who could not hold pressure was a fireman who would be replaced. That pressure drove steam through the pipes to the twin engines, one for the hoist cable that lifted the dipper, one for the swing mechanism that rotated the entire upper body of the machine. A third system, called the crowd mechanism, used a rack and pinion gear to drive the dipper stick forward into the bank. You could not simply drop the bucket into rock and pull. The crowd pushed it in first, forced the serrated iron teeth through blasted limestone under mechanical pressure. The whole machine was a study in converting heat into coordinated force, combustion to steam, steam to pistons, pistons to cables, cables to the dipper ripping through the mountain. The engineer sat in the cab and worked 3 controls almost simultaneously. Crowd forward, hoist up, swing. The bucket tore through the rock face, pulled up and swung over the waiting flat car beside the machine, and the craneman released the dipper door to drop the load, then swing back, crowd in. The rhythm, once learned, could repeat every 45 seconds. A good crew loading from 4,000 to 6,000 cubic yards in a 9-hour shift. A record crew. One Bucyrus team in March 1910 moved 70,000 cubic yards in 25 days. A single machine, 25 days. That record machine and its crew became famous enough that the Canal Record wrote about them. Their output numbers were the benchmark every other crew tried to beat for the rest of the project. But there was a risk built into every bite. The blast crews drilled their holes and detonated their charges twice a day. The rock shattered, the shovels moved in, but not every charge went off. Some sat buried in the rubble pile, invisible, packed with 200 pounds of dynamite, indistinguishable from the stone around them. When the dipper teeth drove forward into a misfired charge, and it happened, the results were immediate and total. There was no warning sound. There was no time to react. The crew of 4 had approximately no margin. This was not a hypothetical danger that engineers worried about in offices. It happened. It killed people. The ground crews laying rail in the rubble ahead of the shovel knew exactly what they were working on top of. Think about what was happening around a single machine while it worked, and then multiply it by 68. The engineers had laid out a system of bench cuts, horizontal terraces cut into the canyon walls at different elevations. each with its own set of tracks. 16 sets of railroad tracks running through the gorge simultaneously, each carrying trains that moved in and out every 60 seconds. The visual scale of 68 steam shovels working in the same gorge at the same time is difficult to picture. Machines the size of houses, stepping forward on their rails every few minutes, turning their upper bodies left and right in the same 45-second rhythm, 68 of them in motion at once across different levels of the canyon wall, all of them exhaling steam, all of their boilers roaring, all of their dippers tearing. Alongside them, 300 pneumatic drills ran constantly, boring holes for the next round of charges, their compressed air exhausts adding a high-pitched, screaming undertone to the bass roar of 68 steam engines. The noise in the gorge was not noise in any ordinary sense. It was a wall of sound that men passed through and never fully left behind. In November 1906, President Theodore Roosevelt made the trip to inspect the project. He climbed into the cab of a Bucyrus shovel on the floor of the cut and worked the controls himself. The photograph taken that day shows him gripping the levers, seated above a canyon that should not have been possible. He understood immediately what he was looking at. Not a construction site, an industrial army, and none of this would have worked without the track shifters. When a bench level was exhausted and the shovels needed to advance laterally to open new ground, the entire railroad network had to move with them. The Americans built specialized track-shifting machines for this purpose. A single track shifter could reposition a mile of railroad 9 feet sideways in an 8-hour day. Engineering records calculated that the same work by hand would have required 600 men. 600 men for one machine, one shift, 1 mile. The Americans had 26 of these machines working in the gorge. The math compounds into something that begins to explain how 100 million cubic yards of rock moved in 9 years. At peak operation, 68 steam shovels worked the Culebra Cut simultaneously. Trains moved in or out every minute of the working day, 160 train loads of material per day, each train running 12 miles to the spoil dumps and returning empty. Every minute, every hour, 6 days a week, for 9 years. The logistical coordination alone staggers comprehension. The man responsible for all of it was Colonel David Gaillard. He worked 12 hours a day in the cut, by personal choice, checking every shovel's output, every section of track, every blast plan. It was said he had saved the government $17 million through relentless attention to small expenses. He drove himself the way the machines drove themselves, without rest, without margin, on coal and will. The machines could handle that kind of pressure. The question, the one Gaillard and every engineer on the project worked to answer every single day, was whether the canyon itself could. Because underneath the math of 68 shovels and 160 trains, underneath the precise choreography of explosions and loading and disposal, the mountain was doing something the engineers had not fully predicted. It was moving. The men who fed the fire, a Bucyrus 95-ton shovel required 4 men to operate and 6 men on the ground to keep it moving. The engineer at the controls, a craneman managing the dipper door, 2 firemen working the boiler, 6 ground workers relaying track, pulling up sections behind the machine and spiking them down ahead of it, racing to keep pace with the shovel's advance. The fireman's job was one of the hardest on the canal. The boiler had no governor, no automation, no warning buzzer. The pressure gauge was a dial on the wall of the cab. The fireman watched it and shoveled accordingly, and the steam demand spiked every time the crowd engine engaged or the hoist pulled hard, which was every 45 seconds, which was constant. If the pressure dropped, the dipper slowed. If the relief valve stuck, you had a problem that made a slow dipper seem like good news. The Panamanian heat turned routine maintenance into an ordeal. Every bearing on the machine needed greasing by hand. The swing ring, the hoist drum axles, the crowd gear shaft, and the heat made lubricants fail in ways Ohio engineers had not designed for. Grease that held in a Milwaukee winter turned to liquid in a Panamanian summer and ran out of the bearing housing within hours. A seized bearing did not announce itself gradually. It seized. The machine stopped. The shovel sat idle while workers crawled into the mechanism with fresh grease and hand tools, working in enclosed steel spaces that were hotter than the gorge floor around them because the boiler was still warm and the sun was still overhead. The canal record noted every hour of downtime. The output numbers that week would show it. No one wanted to be the crew whose numbers dropped because of a bearing. The dipper teeth cracked and bent and sheared off against subsurface rock harder than anticipated. Replacing a tooth meant stopping the machine, climbing out onto the boom arm above the work face, unbolting the broken tooth with a wrench the size of a man's forearm, and bolting the replacement in its place, while the gorge ran at full operation around you, trains moving, other shovels swinging, the whole industrial system continuing its rhythm, regardless of the two men balanced above the cut replacing hardware. The machine was never completely still. The gorge was never completely still. You worked inside the machine while the machine was still breathing. The canal record drove everything. The ICC's own newsletter published each shovel's weekly cubic yard output, and the foreman used the rankings as a whip. Which crew led this week? Which fell behind? Men took it seriously in the way that men take seriously any measure of themselves in conditions that strip everything else away. In Hell's Gorge, with disease and landslide and dynamite and heat as the constants of daily life, being the best shovel crew in the cut was a kind of identity. Some foremen used that pride to push their crews past safe practices, skip a maintenance step to avoid downtime, move back into a blast area 30 seconds early to stay ahead of the competing crew on the next bench. The canal record never tracked injuries. It tracked cubic yards. Most of the men those shovels depended on were not Americans. The labor force in the Culebra Cut was predominantly Caribbean. Workers recruited from Barbados and Jamaica and brought to Panama on the promise of wages that, while low by American standards, exceeded anything available on their home islands. They lived in the zone under a two-tier system that the administration did not pretend to be otherwise. White American workers lived in better housing, ate in better mess halls, received higher wages, and were admitted to the zone hospitals without question. Caribbean workers lived in separate quarters, ate separately, earned less, and when they died were recorded less carefully. The official death toll almost certainly understates the actual number, precisely because of this accounting asymmetry. The men from Barbados and Jamaica were the ones crawling under the machines in the heat to grease the bearings. They were the ones re-speaking rails while loaded trains moved through the cut 12 feet away because the track laying never stopped, and there was no system for halting trains while ground crews worked nearby. A man learned to feel the vibration through the ground before the train appeared around the bend. If he did not learn that, he did not work in Hell's Gorge for long. They had a name for the gorge. Hell's Gorge, they used it without irony. The gorge was their workplace, their residence, and for too many of them, their burial ground. And yet they came. And yet they worked, because the alternative was hunger, and the canal paid. The danger did not come only from heat and noise and exhaustion. The blasting schedule ran twice a day. At the signal, everyone pulled back. The drills stopped. The shovels sat idle. The engineers shut down their engines, and the firemen let the pressure ease back toward idle. In that silence, a silence the gorge almost never had, the fuses went, and for a few seconds the mountain shook from the inside out, and 600 holes in the rock became 600 columns of pulverized stone rising toward the sky. Then the dust came down. Then the inspection crews went in to check for misfires. Then the all clear sounded, and the shovels moved back in. Every man who walked back into the gorge after a blast knew what might be buried in the rubble ahead of him. The unexploded charges sitting invisible in the broken stone, packed with 200 pounds of dynamite, indistinguishable from everything around them. A shovel's dipper teeth could hit one. A drill crew boring the next set of holes could hit one. The workers knew this. They went in anyway because the alternative was to stop, and stopping was not an option. Sometimes a phenomenon the workers called hot rock caused spontaneous detonation, iron pyrite oxidizing in the disturbed earth, generating enough heat to set off a buried charge without any mechanical contact at all. Lightning over the gorge could trigger a circuit. The Panamanian climate made dynamite volatile in ways that Nobel had not designed for. You could follow every rule, account for every procedure, and still be killed by physics you could not control. Gaillard walked the floor of the cut every day regardless, checking the work personally, calculating the outputs, driving the pace. He did not acknowledge fear. Whether he felt it is a different question. For months and then years, the machine worked. The mountain came down in sections. The trains hauled it away. The canal took shape in the blasted stone. But the mountain was not done with them. The warnings had been there since 1907. Small things, cracks in the clay walls, seams of water working through the rock. A tremor felt through the floor when the right layer slipped against the wrong one. The operators noticed. The engineers measured, and the mountain waited, patient in the way that mountains are patient for the moment when the weight of the wall above outran the resistance of the clay below. Then it moved, the day the mountain fought back. October 4, 1907. A crack appeared in the canyon wall at a section called Culebra Cut. It was not dramatic at first, a line in the clay, a seam opening. By the time the crews registered what was happening, 500,000 cubic yards of mountain were in motion, not falling, moving, the entire mass of saturated clay sliding forward in one piece slowly, unstoppably, like a glacier made of mud. It filled the bottom of the cut 20 feet deep. Gaillard looked at it and called it a tropical glacier. The clay was too soft for the shovels to bite. They washed it out with high-pressure water hoses, which is to say they tried to undo the mountain with a garden hose. It took months to clear, and the mountain went back to watching. Over the next 6 years, it would do this 100 more times. Slides of every description. Gravity slides where saturated material ran down over harder clay, deformation slides where overly steep-cut walls collapsed inward under their own mass, creating bulges that pushed up from below the canal floor itself. Some slides crept slowly enough that the crews could pull equipment back before it was buried. Some gave no warning at all. The worst came in the night, when the accident whistles screamed across the gorge and men ran toward the sound carrying lanterns, heading into the darkness of a canyon that had just moved, knowing that somewhere in the rubble their workmates might still be alive, digging with their hands, because the shovels were buried too. The slide at Steam Shovel Row was different. It did not come all at once, it crept. In January 1910, surveyors noticed that buildings along the settlement at the edge of the cut were shifting, not dramatically, inches per week, then feet per month. Steam Shovel Row, where the shovel crews lived, was moving toward the gorge in slow motion. Engineers set stakes. They watched the stakes move. By November 1910, the buildings closest to the edge had to be dismantled and relocated. Workers carried their own housing piece by piece to higher ground. They rebuilt, assumed the problem was solved. In January 1911, the slide reached where those buildings had stood and kept going. The relocated buildings were dismantled and moved again. Eventually, 75 acres of the town of Culebra slid into the cut. A whole neighborhood in geological slow motion, consumed by the mountain they were cutting through. The mountain was not just fighting back at the work face. It was reclaiming the territory above it. Steam shovel number 258 was working the cut on May 29, 1913, with a full train of loaded flat cars beside it when the wall behind it came down. The photographs that survived show the machine half buried in clay, the flat cars crushed and tilted at 45 degrees, the entire scene serene and terrible in the way that disasters are serene once the screaming stops. There is no record of whether the crew of number 258 survived that specific slide. There is a record that over the course of the project, the slides moved 30 million cubic yards of extra material into the cut on top of the 100 million that were supposed to be there. 30 million cubic yards of mountain that the shovels had to move twice. But the slides were not the worst of it. The slides at least gave you something to see. The dynamite gave you nothing. December 12, 1908. 11 in the morning. The west bank of the cut at Bas Obispo, where a drill crew had prepared charges in the rock the evening before. The signal had already been given for work to resume. Men were back on the floor, shovels were loading, and then two explosions, almost simultaneous, set off a chain reaction that detonated 44,000 tons of dynamite in a single event. The gorge disappeared inside a column of rock and smoke that witnesses described as reaching the clouds. When the debris came down, it came down across the entire width of the cut. Men and steam shovels were thrown across the gorge. A machine weighing 95 tons was moved by the blast. The explosion filled 60,000 cubic yards of the canal with rock and debris, piled 20 to 30 feet deep in places. The accident whistles screamed. Men from adjacent sections came running because that was the system and that was the code. And in Hell's Gorge you ran toward the whistle. They came with lanterns and stretchers and bare hands. Electric lights were brought in by the time darkness fell. The emergency lighting rigs they kept staged for exactly this kind of work. And the search continued through the night. Shovels that had been working other sections of the cut were redeployed to clear the debris pile, swinging their dippers not into fresh rock but into the rubble of the blast zone, moving stone by stone to reach wherever a man might still be alive underneath. Some were. Most were not. When the count was made, 26 men were dead and 49 were wounded. Chief Engineer Goethals reported that the cause appeared to be acidic water in the blast holes. Some engineers involved believed the actual cause was never determined and never would be. The phenomenon of hot rock, the volatility of dynamite in the tropical heat, the possibility of a lightning strike. None of it could be ruled in or out. The cause was never found. The dead were buried. The shovels went back to work. This was the mathematics of the Culebra Cut. 5,609 workers dead over the entire construction period. And that is the official American number, which historians believe significantly undercounts the Caribbean workers whose deaths were not consistently recorded. Of those confirmed dead, 4,500 were non-white. The men from Barbados and Jamaica who lived in separate quarters earned less money and were counted less carefully when they died. The journalist Arthur Bullard wrote that never before had man dreamed of taking such liberties with nature. He did not finish the sentence. He should have added, and never had men been taken such liberties with. The shovels did not stop for any of it. 600 dynamite holes a day, twice daily blasts, 160 trains. The pace was relentless because the pace had to be relentless, and Gaillard drove himself the hardest of all. By 1912, the men around him were noticing something wrong. He had always been thin. Now he was gaunt. He made errors he would not previously have made. Small administrative miscalculations, lapses in a memory that had been legendary for its precision. He attributed it to exhaustion. He had been working 12-hour days in the floor of Hell's Gorge for years. It seemed a reasonable explanation. It was not exhaustion. In 1913, he was promoted to colonel. 1 month after his promotion, he returned to the United States, suffering what he described as nervous breakdown brought on by overwork. He was admitted to Johns Hopkins Hospital in Baltimore. On December 5, 1913, at the age of 54, Colonel David Dubose-Gaillard died of a brain tumor. 9 months before the canal he had built opened, he was buried at Arlington National Cemetery. The cut was renamed in his honor in 1915. You know it today, if you know it at all, as the Gaillard Cut. The mountain had taken him too, not with a slide, not with dynamite, with something smaller and slower and more patient than either. The shovels kept working after he was gone. Where two shovels met. May 20, 1913, the bottom of the Culebra Cut. Two Bucyrus steam shovels working from opposite ends of the 9-mile gorge, each advancing toward the other through blasted rock, had been narrowing the distance between them for years. Shovel number 222 from the south. Shovel number 230 from the north. They had each moved more than 1 million cubic yards of material over the course of the project. Each had survived slides, broken teeth, failed boilers, flooded tracks, and the 1,000 other ways the gorge attempted to stop them. On that morning in May 1913, the two machines came face to face at the bottom of the cut, 40 feet above sea level. The crews climbed down from their cabs and shook hands across the rubble. The photograph taken of this moment shows the two shovels nearly nose to nose, their booms lowered, steam still rising from their stacks. Two machines that together had moved a continent's worth of rock, stopping at last to acknowledge each other. It is not a dramatic photograph. It is just two machines and some men in a canyon. But understand what those two machines represent, and it becomes something else entirely. The final push to that meeting point was not easier than the years before it. The gorge walls in the last section were among the most unstable in the entire cut. The same clay formations that had produced the Cucaraca slide in 1907 ran beneath both approach paths. The two crews had been advancing through ground that the geologists had flagged repeatedly. Slides came without warning in the weeks before the breakthrough. In the 48 hours before the two machines met, engineers were watching 3 separate sections of wall that had begun to show movement. The men in the cabs knew this. The ground crews knew this. The shovel advancing from the south had lost 8 hours the week before, when the bench directly above it cracked along a seam, and the track had to be rebuilt on repositioned ground. The last few hundred yards of that 9-mile gorge were not a victory lap. They were the same gamble, at the same odds, that every yard had been since 1904. The two crews shook hands across the rubble because they had survived it, not because it had stopped being dangerous. Before the Panama Canal existed, a ship traveling from New York to San Francisco had two choices: cross the continent overland, with all the cost and delay that implied, or sail around the tip of South America, Cape Horn, 8,000 miles of extra ocean, months of additional time, storms that had been killing sailors since the age of sail. The canal turned that 8,000-mile detour into a 50-mile passage, not a minor improvement, a transformation of the economics of every ocean-going trade route in the Western Hemisphere. The ships that crossed through on their first transit were not just passing through a waterway. They were passing through the answer to a question that had been asked since the first European looked at a map of the Americas and thought, there has to be a way through. The French had worked 9 years and lowered the Culebra summit by less than 20 feet. The Americans removed over 100 million cubic yards of material. The entire American excavation phase moved 240 million cubic yards of rock and earth in total, enough material stacked in a square mile to stand 251 feet deep. The project cost $375 million, the most expensive construction undertaking in American history to that point. The canal opened on August 15, 1914, when the cargo ship SS Ancon made the first transit. The war in Europe had already started, which is why the planned grand ceremony was cancelled. The world was too busy beginning another kind of engineering project, one that also ran on industry, organization, and a willingness to pay in men, to properly celebrate the completion of this one. Consider what that payment actually looked like. Of the 5,609 confirmed dead, 4,500 were non-white West Indian workers. The men from Barbados and Jamaica who built the canal, who fed the fires and spiked the rails and worked the rubble piles, who lived under a two-tier system with separate housing and lower wages, they paid in proportion to their conditions. They made up the majority of the labor force. They absorbed the majority of the casualties, and they received almost none of the credit. The official narrative of the Panama Canal is built around the engineers and the shovels and American organizational genius. The men who did most of the actual work in Hell's Gorge were largely erased from the story the moment the SS Ancon passed through. What the Culebra Cut accomplished, stripped of ceremony, was this. It proved that industrial machinery coordinated at scale could do what no army of men with hand tools ever could. 102 steam shovels on rails, moving in concert with a railroad system built to haul their output. This was the answer to a problem that had defeated the greatest engineer in the world. The trick was not one machine. The trick was making 100 machines move like one machine, in a system so tightly coordinated that a train was always waiting when the bucket swung over and another was backing in before the first had cleared the cut. That system, machine plus railroad plus the human beings who kept both running under conditions that should have stopped them, was the real innovation of the Culebra Cut. Stevens understood it. Gaillard executed it and paid for it with his life. The West Indian workers sustained it with their labor and their lives, mostly uncredited, largely uncounted. The Bucyrus design that dug the canal is gone now. Diesel came in the 1930s, smaller and cheaper and safer, and the coal-fired steam shovel was retired to museums and scrapyards within a generation of its greatest triumph. The hydraulic excavator that replaced it can be operated by a single man from an air-conditioned cab, without a fireman, without a coal supply, without a ground crew laying rails ahead of it. It is better in almost every measurable way. Most of the shovels were scrapped in Panama. A few made it back to the United States. A surviving Bucyrus Model 50B ended up in Nederland, Colorado, where it was used in placer mining until 1978 and now sits preserved in a local mining museum. The canal itself was handed over to Panama in 1999 and continues to operate today, handling over 14,000 vessels a year. The Gaillard Cut still carries ships across the Continental Divide every day. The walls have been cut back and stabilized in ways the 1904 engineers could not have managed. The landslides still happen occasionally. The mountain did not stop watching. It just learned to accept the cut. There is one detail that seems worth holding on to. When the Americans completed the excavation, they found in the rubble a bushel of dynamite left behind by the French in 1887. It had been buried in the rock for over 20 years. The steam shovel crew that dug it up reported it had lost its potency. 20 years in the mountain, and it had given up its force. It would have fit right in. They don't build machines like the Bucyrus 95-ton steam shovel anymore. The engineering problems they were built to solve have been solved more elegantly. But the problems themselves, the scale, the isolation, the indifferent mountain, the daily calculation of what you are willing to sacrifice to make something exist that did not exist before, those have not changed. What the Culebra Cut proved is that with enough machines, enough coordination, and enough willingness to absorb the cost, you can move a mountain that the greatest engineer alive said could not be moved. You can rewrite a map that sailors had been using for 300 years. The price was paid in full, most of it by men whose names were never recorded. The men who fed the fire in Hell's Gorge understood that calculation in a way that is difficult to explain to someone who has never stood at the bottom of a canyon at 120 degrees and listened to a steam shovel eat rock while the wall above them trembled. They were not heroes in the way the histories tell it. They were workers, most of them from Barbados and Jamaica, underpaid and undercounted, largely forgotten the moment the SS Ancon cleared the last lock. But the canal is there because they were there. The ships are crossing because those men were in the gorge, in the heat, loading trains every 60 seconds, waiting for the mountain to move. It always moved eventually. They just moved more.